Okay, okay, it's recording. All right. Okay, hi everybody. Okay, so today we're gonna try to do um, neural network is taken by this Francois Chollet, right? Francois Chollet deep learning. Um, so he got a really good book. He's I think one of the Google researcher for deep learning, right? So you can just go to GitHub, right? And then just fork it. Yeah, just fork it. And then we are going to look at the first look at neural network. This one, the first um, lesson here. Okay. Um, no, actually, wait. Are we gonna look at that one? Yeah, yeah, yeah. Okay. So what you want to do is you go to Google Colab, right? If you haven't done it, do so. Just colab.research.google.com. Yeah, and then you put this um, the your URL. Once you fork it, so you fork it, and then you just click this, all this, and copy and paste all of this thing, and then you can just put it under click on GitHub, right? And then just click over here, right? And then it's gonna open a window, okay, a new window over here. And here we are right now. And then you want to just make sure the runtime is on GPU so it's faster. Otherwise, it's gonna take some time. Change runtime tab GPU, right? Do not use TPU because I think this is just for it's designed for um, GPU, not TPU. Okay, so you can try it, but I don't think it will work because from what I understand, the TPU, at least for now, if you want to use the TPU, the API is still different. It uses like keras.tpu something instead of just keras, right? So we can start to run this. So a background. So this is like a hello world for neural network. So we have uh, what do you call this? We have a data. It's called an MNIST data set. Is basically a classic data set in the machine learning community uh, to uh, to identify images. Sorry, yeah, images. So I think it's sorry, to identify numbers from I think from 0 to 9, right? So we are going to classify, train the neural network so we can get a nice model. So that model, once we deploy it in the real world, it can classify. Um, so you put in numbers, and then the model or the neural network can classify which of the 10 categories of those numbers. Is it from 0, 1, 2, 3, 4, 5, 6, 7, 8, 8 or 9, right? So the training data set is called MNIST, right? So this is like the hello world for the computer world. Um, so it consists of 60,000 training images and 10,000 test images. So that's quite a number of them. This data is from National Institute of Standard and Technology, right? The NIS basically in the MNIS. I do not know what M stands for. Interesting, right? Okay, so we are going to run the first one. So we already did this import got crash. So you press just shift return, right? If this is the first time for you to use Google Colab to run it, there are two methods. One, you can just click this play button, right, to run the cell, or you can use shift return. I think I'm not sure if it's the same for Windows. It could be the same. You can try it on, or you can just yeah. I think that's. I'm not sure if you can run it from here to file runtime. Okay, you can run it from here. I'm not sure. I haven't tried this one. It is run all. Okay, no, but I prefer the shift enter. That's just for me. Okay, shift enter. So it's just 2.1.6. So we are importing the amnes right now. Yeah. So we have basically train images, train label, task images, and task label. Yeah. So we are calling this amnes load data function. So if this is the first time like you for you in into Python, Python is a very high level programming language. It's practically the de facto in a deep learning community or in machine learning, right? So if you're, I think it's safe to say if you're still hesitant whether to use Python or not, just yeah, Python I think is the way. That's just like the short answer. Um, okay, so we're just calling the amnes object to load, right? The load data is like you can think of as a function, or I think in a Python word it's called like a no, because it's an objective programming, like object oriented. So yes, they don't call it function. They call it more like a, I forgot what it's called. Anyway, so um, if you're not new to object oriented, once again, think of everything in Python basically is like an object, right? It's like a object is in the real world could be like a person, a table, a house, a car, right? So amnes, so in inside that object you have like the properties, the character of that object, and he has what you can do in that object, right? What you can do in that object is basically the function, what you can operate on, right? Um, so one of the function is called load data, and then it gives you basically train images, train label, and everything, right? So and then you can check um, you can check basically what is the shape of those train images, right? So just dot shape. So it gives you 60,000. There's 60,000 of those training images, and then it's 28 by 28 pixels. Yeah, so if once for this or your new image basically it's a bunch of pixels, right? So for this case, this number images it consists of 28 by 28, so 28 rows and 28 rows and 28 columns, right? So think of it like a matrix, like a box, like a square, where it has 28 rows and 28 columns, and each of those rows and column is a numbers, right, from 0 to 55. Well, 0 is like the darkest pixel, so it's like completely dark, and then 255 I think is the lightest one. I think that's correct. I might be like mistakenly um, like the other way around. But I'm sure 0 is like dark, and then 255 is the lightest. Um, why 0 to 255 is just the way it is. I think it's 2 to the power of 8 because it's using I think it's 8 bits, right? Um, so anyway, so we can len is counting how many train labels are there. So it's also 60,000. You can also execute train labels, right? It's basically a NumPy array, right? Um, so and this is basically inside those images. Um, sorry, this is just a label, and the label is from 0 to 9, right? Um, 0 means it's the image is 0, 1 is the image is 1, and so on, right? So let's take a look at the, okay, I'm just gonna make sure I'm gonna run this trend level array, okay, and then the shape of the test images is 10,000, 28 by 28, and then the length of the test label, 10,000, and then the test label itself, right? This is like the answer, right? So basically, neural network, when you want to train the neural network, uh, you need to have quite a number of data, and there are two things of data that you need. One is the training, one is the test, right? Later on, we'll get more complicated. There's actually in the training data, there's data that's so-called as validation data, meaning you are just want to be sure before you deploy it to the real world that you are your model is not underfitting or overfitting. It's like generalized really well. And that concept of underfitting and overfitting, it's a very very big concept in machine learning world or deep learning. And there are tricks or techniques how to um, minimize the overfitting or minimize the underfitting, right? Um, One of the tricks is to divide the training data into two sets, which is the training and validation data, right? So once you already train it, but in this case, we don't divide the training into two. We just put everything into training, which is 60,000, I think. And of course, the test, right? Anyway, we can talk that later in probably the next session. So now we are going to import the model from keras and import the layer. So um, as you know, a neural network or deep neural network is basically there are models, right, that you are need to choose, right? There's several models, right? Whether it's a sequential, whether it's a recurrent neural network. So there's many architectures, and for each of the architectures, basically there are how many layers do you want it to be? How deep, like how deep do you want the neural network to be, right? It is like just because you have the input here, right? The bunch, the pixel 28 by 28 images, right? So that's the first layer, right? Basically, and then you have the output layer, which is basically the to classify from 0 to 9, right? So there are 10 10 outputs, right? To classify that. And then what's the one in the middle, right? So you need this thing, right? The one in the middle, at least one. So to extract. Um, I don't think if you can just input and output because you need to a way to process the information. So you need something in the middle, right? So at least you need one, right? So so we already imported. So the network models that we want is it's called sequential, right? Like I said, there are different kind of models that we can use, but for now, is sequential. Is meaning just uh, feed forward. It's in sequence instead of there are models that are being used for, let's say, a time series uh, dependent data or information. For example, you want to forecast, for example, a stock. So if you want to forecast a stock, uh, the, uh, the output or the prediction of that stock is really depending on the history, right? So if you want to, for example, predict the stock, like what is the stock of Facebook for today, then you want to know like what is the history, right? You cannot just get just one day before that. You want to know probably like 100 days before that. You want to know like the movement of the stock. So that's like a time series dependent kind of a uh, yeah, predictions. And for that, you need to use a different kind of model, right? So for anything that's not time dependent, so in this case, we're just going to predict, well, we're gonna put all of a bunch of images, and then I want the model or the network just to predict what are those images. Is it from 0 to 9? That's it. So there is no time factors in consideration. So that's why we're just using sequential in this matter, right? Of course, the sequential model can be used for other things, not just for um, image identification, right? But in general, anything that has nothing to do with time, you can use sequential. It's there. You can use that, right? But one time's already in play, then you have to think something else. Yeah. Yeah. So that's the model. Now the second, this one, the second, this is the layer we're talking about, the one that in the middle. We need to have at least one layer. So, and for this purpose, we have two layers, right? You can have just one and try it out, see if it works, right? So the first layer here, it says there's 512. I think this refers to the 512 neurons inside that layer. So how many neurons do you want to put? It's really up to you. But there should be like the more number of layers, the more complicated it is, the more complex it is, the neural network, right? And the more complex it is, the more it needs time to train, and it needs also it's more expensive in general, right? So you kind of have to balance that thing. You need to have some kind of intuition, and this I think this is the value of experience. That's why if you want to work, let's say you work in the industry, and then some companies they ask for at least, I don't know, 5 years of deep learning experience. So because in experience you have that intuition whether you want to use like only like 200 neurons or 500 neurons or 600 neurons, right? It's not like a straightforward answer. It's more like a right now it's more like an art than a science. That's why it's so this area is so intense. It's so amazing still, right? So people can like be it's very experimental, so to speak, right? It's not very like hardcore science, right? Has to be like 200, 300. No, of course there is like a rule of thumb, but it's not straightforward science. Um, like recently, there's a new conference of the neural network, or and I think NISP recently. One of the team is basically asking the question whether is neural network an art or a science, right? Or it's a combination of both, right? So anyway, so we choose to have 512. Yeah, we can play around with this and see what happens if we still have time. The activation is ReLU. ReLU is the activation function. So that it's normally being used right now as I speak. Okay, probably a year from now or 6 months from now, there's going to be another research that disprove that ReLU is not effective anymore. There's another algorithm that is more effective. Then we use something else. But another activation function that I know of is 10H, sigmoid, right? And this is really important if you are new to a neural network. This is what makes the neural network as a universal uh, algorithm, approximation algorithm. It's a universal algorithm. You can use this algorithm for anything, not just for one specific use case. The activation function, it makes it it is introducing non-linearity to the function as compared to just a linear, and that's make it so powerful. This makes the neural network can detect human faces, can detect within the difference between dog and cat, can detect things that are intuitive for human before, like really, really easy for human. Like, we are very good at recognizing people. We are very good at recognizing images. But for computer before, the deep neural network um, uh, era, they cannot do this. So people try to hard code, right? To just use rules, many rules. Like it fails, right? It cannot do it until I think Geoffrey Hinton introduced this inspired neural network inspired by the our how our brain works, basically. Yeah, that's why it's called neural network, right? So the activation, I cannot tell you how much this activation function is really important. It's like the one, it's the one thing, the one factor. If you have to, take take it away from this, I don't know, 40 minutes, 50 minutes of YouTube session, the one thing that you have to remember that this is the one that makes a neural network works. It's basically introducing the non-linearity. The non-linearity function is basically the activation function. And you might ask why is that so, right? So if you look at all of the layers without the activation functions, all the neurons is basically a linear functions. If you still remember the high school math, it's basically to, let's say, to compute, to compute a line. Basically, you have, for example, uh, housing prices to predict housing prices, right? Based on, for example, the number of square feet. If the number of square feet is 100 square feet, then the house price is 100,000. If the square feet is 200,000, then the housing prices is 200,000, and so on. So you're trying to find a line. Do you still remember the equation for a line? It's y equals to mx plus b, right? So basically, you're trying to find the m, for example, the tangent, and the b basically is. So if once you find the tangent, right, whether it's like this or like this, the how the y over x, the tangent, right, is 2/3, 1/3, 1/4, 1/10, right? Once you find this, and then you also have to find the b. The b is the one that's make the line move up or move down, right? On the y, on the xy plane, right? So that's it. The neural networks, all the neurons, that's what it does basically to compute the parameters of the y equals to mx plus b. That's about it, right? So so when we talk about machine learning, what is our backpropagation function or gradient descent? All it does when we backpropagate or using the backpropagation algorithm is to find the right parameters, or they call it the parameters. The parameters is basically this the m, right? That's in a linear regression in a high school math. It's the m. Yeah, you know the x, you know the input, and you know the output, right? The label, right? And so y equals to mx plus b. So you know the x, you know the y. You have to find the m and b. So m in a high school math is y over x. Basically, is the tangent, the like how what is the inclination of your line, right? So that's the parameter that the machine learning is trying to find out, the m, basically, right? In machine learning, we call it weights, right? It's just a different term, but it's the same thing. So and plus the p, right? In a machine learning term, the p is called the bias. Yeah, I think it's the bias, right? So that's it. That's about it. You have to find the w, the weight, which is basically the tangent, and plus the b, and everything is a linear. So if you and over here we have two layers. So and if you don't introduce activation function, which is to introduce nonlinearity, then it's gonna be just a line, right? The function is gonna be from one line to a bigger line, probably, but it's gonna be a line, which means your function is just a linear function. It's not It's not good for non-linearity of prediction. It means you cannot like ask your neural network to predict the face of a person, because the face of a person is non-linear. Yeah, right. Not linear is just means every time you the proportion of the output is always in proportion to sorry, the proportion of the output is always uh, in proportion to how much you introduce to the input. That's what linear is. That's why it's making a line, right? So that's why it doesn't work. So I hope you understand the intuition. It's like if you want to make think a different way, right? So y equals to, let's say, 2x plus 3, right? That's linear function. So it's a line, right? But think about it, uh, 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 higher, what do you call it? Higher variable. Sorry. So higher level of dimension, meaning you introduce square, or to the power of 3 or to the power of 4. So if you imagine, if a function is like y equals to x squared, right? It's not linear anymore, right? So the function is going to be probably like a hyperbolic, or the opposite. So it's not linear, because the output is not in proportion to the input anymore, right? If you introduce a higher dimension, x to the power of 3, it's even nonlinear, right? Like a sinusoidal, like a function. That's one example of nonlinear, right? So you can think it from that angle. But for me, the most like common sense angle, if you can think of it like a, you can think of it like a uh, introducing like a, yeah, like a mask, like a mask, and a mask of a cat. Let's say you want to uh, um, predict if it's a cat or not a cat, right? So you can think of it as the mask of a cat, right? And the mask of a cat has a contour, and all each of this contour is like a valley, and like a mini mountains, has many valleys and mini mountains, and all of those things are non-linear basically. Or you can think of it as a, um, um, when you're drawing like a chart, right? So if it's a linear function, you're just drawing a line, right? And I got this, I think, from OCD level. OCD level is a really good podcast of understanding the intuition of deep learning and machine learning in general. So linear function is just drawing a line, psh, right? But for deep neural network, is drawing a bunch of lines like a Zorro. You draw many lines, right? And every time the lines connect, you introduce a wiggle. Do you understand what I mean? So you wiggle it. So you just Zorro, they make many. He makes many lines, right? Uh, if to the data points, right? And then and then each of those intersections you introduce a wiggle, like a curve, instead of just, if you cross one line to another line, instead of the intersection is 90 degrees, you make it like curvy. And that's what non-linearity function does to to the uh, to the whole network. And that's why they call it a universal function approximation, right? Because you can just put anything there and it can detect anything, kind of, right? Okay, enough of that. So the input shape is 28 by 28, and then the second layer uh, over here is, so, oh yeah, we haven't talked about this dense, right? What is a dense layer? Dense layer is basically means the layers, the neurons that are on the output. Let's say you have three layers, right? So first is the input, right, where all the images 28 by 28 goes, right? And then the output layer is basically the classification there, what 10 neurons because we want to classify into 0 to 9, right? And then the middle layer is the deep neural network. In this case, we have two, basically, two middle layer, right? Just for the sake of simplicity, just think about just one. So dense layer, basically the neurons on the uh, uh, before that, uh, it will be connected to every neurons to 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 the next layer and to the previous layer. So for example, if you take the neuron in the middle, that neuron will be connected to every neurons. So if there is like a 28 by 28, which I don't know, 500 something, or probably there's 500 neurons of the input, right? So if each of that neuron will be connected to every neurons on the previous layer, and also connected also to the every neuron to the next layer. That is what a dense layer is, right? So it's kind of like to make it very kind of complex, so to speak, and that's basically also inspired by how our brain is wired, right? Our neurons is wired in our brain. Okay. Um, okay. It's also called a fully connected layer, right there. So the second layer has only 10, um, and then the activation is a softmax. Um, oh, the second layer, sorry, the second layer over here is already the output. It's using softmax because softmax is like a kind of like a probability probability um, um, it turns numbers into a probability from 0 to 1. That's what softmax is. And you can think about it uh, in visually think of it if you have a bunch of numbers, right? I don't know, from 0 to 10, whatever, right? And then it's not in a probability distribution anymore, right? So some of it is like 9, some of it 1, some of it like zero point 0.1, some of it like 3. So what the softmax does is basically trying to pull the maximum number. If the maximum of that number is in 9, to pull it really really high, and to kind of depress the number that is low to make it soft. That's why it's called soft and max. So then the numbers that are high is going to be pulled even higher. The number that is low is going to be being depressed, and it will turn everything into uh, probability and into summing into one. That's what softmax is. So its score will be the probability that the current digit image belongs to one of our 10-digit classes. Okay. So okay. So that's the model. We're gonna run it, right? And then to make our network ready for training, we also need to pick three more things, right? So first is the loss function, right? So once you train it, you have to you predict the y, right? Uh, based on the label, right? So yeah, and then sorry, you once you first um, put all of the first batch of the training data, right? And then you have the y prediction, and then you have to compute how far that y prediction is to the label, right? And that's called the error, or right, or it's also called loss, right? And we need to compute, we need to backpropagate using a loss function, right? Um, so this is where all of the backpropagation algorithm comes in, and the gradient descent basically is trying to um, tune in the weights and the biases, right? Okay, so so we have to pick three things on the compilation step. one is the loss function, one is the optimizer, and one is the matrix to monitor during the training and the testing. Here, the matrix we use is accuracy, how accurate is our model is, right? So here is the network.compile. So we are using for optimizer, RMS prop. Again, there's a bunch of algorithm that uh, you can use. I think this is one of the most common one, and probably is the most probably also like um, accurate kind of. And then the loss function is categorical cross entropy. The matrix we use is accuracy. Okay, so this is the network compile. So remember, we are not even training yet. We are just trying to define the model, right? The model, the architecture, right, of the neural network, right? Okay, so before the training, we have to pre-process. This is the thing that's um, really important, is our ability as a deep learning engineer, or if you want to become a machine learning engineer, you need to be able to pre-process your data. And from what I heard, I'm not really a deep learning practitioner as of now, but from what I heard, this is actually the major bulk is going to be if you are going to be practicing in this um, area. That you are not going to be spending a lot of time in like building the model. Building the model is kind of probably the easiest stuff, or is also the least amount of time that you have to dedicate. But you have to dedicate more time on the like on the prep side. Like uh, you have to understand the data more, like how is the data is going to be like fit in, and how do you are you gonna pre-process the data because you cannot just fit in the data to the neural network. It just doesn't work. Neural network just wants to accept a specific format, right? So you have to be able to reformat the data, and that reformatting the data is called pre-processing, right? So in this case, so what is this? We transform the data into a float 32 array of shape with values 0 to 1. So remember we talk about the original pixel is 28 by 28, right? And then the values is basically from 0 to 55. That's just how it's the standard of the industry is, right? From 0 having is the darkest to 55 is the brightest of the pixel, right? Um, Neural network only accept 0 to 1. That's just the way how computer um, I think the neural network works, right? Um, Especially if you talk about computers just understand binary numbers, right? 0 and 1, right? So I think this this is part of the reason why. So you need to scale all the values through 0 to 1 interval instead of 0 to 55. This this particular process called scaling or nominalization, I think, yeah. And then there's different kind of technique depending on the domain that you're in. For this example is an image, right? So you just kind of divided everything by 255, from like 0 to 55 and to 0 to 1, you kind of divide by 255, or you can like I think that's kind of, yeah. But if you go to a different domain like LSTM, the data that's depending on a time series, depending on time, it's going to be a different technique, I think. So so previously in our training, is the data is 60,000, right? And shape 28 by 28 is a type UNTI-8 is a type of data type, is a I think integer with values from 0 to 55 interval. So we want to make it into float 32. Float means decimal points. There's decimal. That makes sense. Right? If you want to make it 0 to 1, that means there's like 0 0.5, 0.32, 0.216, 0.118, So that's what float is. Okay. Okay. So this is the just the the instruction how to do it. First, reshape it, and then and then so this is divided by 255 and float 32. Yeah, I do not know what does this do, reshape. Yeah, why not just directly? But I bet it does something there. Yeah, you can take a look at it actually. So if you want to take a look at the, but probably we don't have time. Anyway, we just trust the code right now. If you want to, I think just run this on your own, on your own time, and then you can just like separate it. For example, you want to see what's um, the output of that, right? And then you can just like yeah, you can just see it. Oh, it doesn't do. Yeah, you can. I think you can just print it, and then you can see what it looks like actually the data. So you can have a better understanding how is being pre-processed. But in this case, it's just showing you like 0000 whatever, right? You can like do, for example, compare it with this, for example. I don't know if it makes sense. Um, like before and after. If you want to know like the nitty-gritty what's going on, right? Yeah. Or you can read the documentation, right? So in this case, just give you ideas how to like understand what's really going on. But yeah, but the most important thing, you kind of know what are the main steps and right intuitively. Okay. So next step, we also need to categorically encode the labels, a step which we explain in chapter 3, categorically encode the label. So we need to categorically encode the labels. Okay. Well, we just take it as a face value as of now. So we need to categorize the label. Okay. Yeah. So I think my intuition is so um, so yeah, um, this is I think it just has to do probably with turning all those numbers into like vectors numbers. I think I'm not sure what is the categorical label. I know that from a different domain, like from the when you want to try to predict um, the sales forecast, for example, for grocery stores. And some of the data, so for example, you're trying to forecast the grocery stores, and um, you have like a bunch of features. For example, the year, the the season, whether it's fall, spring, at what year. You have like the distance from, for example, from the house. Um, there's a bunch of features to predict like the sales, and you can actually turn, even though if it's a year, it's a number, for example, but you can turn that into a categorical, which because year, it doesn't make sense if you for example if you assume year as just like numbers, because year like um yeah anyway that's for a different okay. So now we are ready to train the network, right? So to train the network, we call it fit. So we call it network.fit. We put the train images, right? We put the train label. Remember this, again, in machine learning, there are three, right? Basically supervised, unsupervised, and reinforcement learning. So this is just one of the branches of supervised. Supervised is just basically training the network using label. So you kind of like being a teacher to your kid, and you tell your kid Okay, this picture is a cat. This picture is a dog. This number is 1. This number is 2. That's supervised meaning. But if it's unsupervised, you just show the pictures and you just be quiet, right, to your kids. You just keep your mouth shut. You don't say anything, and then the kid will try to like probably trying to rationalize itself. Oh, what is that? Is trying My dad is trying to show it to me. So that's unsupervised. Reinforcement learning is a different thing. It's basically based on actions, kind of, and reward. You just tell it there's a goal, right? And then you want the network to take action, and if it's like doesn't reach that goal or doesn't close contribute close to that goal, you either reward or punish. That's kind of the idea of reinforcement learning. Okay, so now we're gonna do this. So there's the images, there's the train label, there's an epoch. Epoch 5. Epoch is the number of iteration, number of. So we have 60,000 images, right? So when you feeding the network all of the 60,000 images one time means you feed it one time 60,000 to show to teach the network, and to compute all of this the weights with backpropagation algorithm, right, with the compile function, right? It's called one epoch. You show it the second time, the whole batch. I'm talking about the whole 60,000. The second time to the neural network. That's called epoch number 2, right? Including with the backpropagation. So this is the idea is to, as you increase the number of epoch, you want it to be the accuracy to be higher and higher. Because remember, the intuition is the first time the network is dumb, kind of, right? Because the weight is being like initialized kind of like randomly, right? So it has the parameter is just like screwed. If you think about like line, for example, if you have a bunch of data, the line is like way off, right? And then as you feed forward the data through the network, the line becomes like, if the data is here, the line will become like gradually like closing to the line. One epoch, two epoch, three epoch, four epoch, and then hopefully by five epoch it's there. It's giving you the right model, right? So that's the idea. So here we are using five epoch, and the batch size 128. So um, that's 128 images, I think, every 128 images, right? So you put like one images, right? So there's 60,000 images. You put the first images, boom, to the network, and then the network will compute the error, and then based on that error, we'll try to update the weight and the weight and the biases, right? And then the second images you feed forward, right? And then you do the same thing, right? You compute the error, and then try to update, and then update the weight and parameters and the third images. So if you do this for 60,000 images, it's going to be expensive, right? Because it's going to be like 60,000, you have to do adjusting of the weight and the parameters. And that, not to mention like how many actual parameters we have to update, because it's not just 60,000 times. No, it's 60,000 times the connections. Remember, it's a dense neural network, right? So every neurons, and even in this case, our deep neural network has 128 neurons in a middle layer, and every neuron is connected to the input and connected to the output, and every of those connection has weights and parameters, right? So it's not just it has to be 60,000 times, I think, 128 and times times 10, and then so it's going to be like millions of parameters you have to adjust. That's computationally so expensive. Okay, So we don't want to do that. So we have to kind of cheat. The way to cheat it, instead of every image you have to update the parameters, right? You do it every 128, kind of. How does it do it exactly? I do not know. Probably kind of average it, you know. I'm not sure. Yeah, the technicality of that, I'm not sure. But this is like taking a batch of 128 images, you know, put it on the feed forward, and then you compute kind of the. I think that's what it does. Okay, so we are going to run this. Oh, what's happened? Okay, okay. So first, the accuracy is only 11%. It's not good actually. I don't know why it's only dot 11. Hmm. Okay. Yeah. Two quantities are being displayed during the training loss of the network over the training data and the accuracy of the network over the training data. We quickly reach 98% on the training data. Now let's check that our model performed well on tests. 98%? Are you serious? I think it's not. I don't know. There's something is not right. I'm not sure. It's really low, 11. I think there's something I didn't do. Let's do it from the beginning, okay? Let's do it from the beginning. Okay, so we import that one. Okay, and then we import the MNIST data. Turn images. And yeah, I don't know why it's only 11%. Oh, there you go. Yeah, I don't know why now earlier is only 11%. Now it's much better. So you can see the accuracy is increasing from 92% to 96 to 97, 98, and then 98, right? Okay. Yeah, I must have skipped something. Okay, and then now we are just getting the network evaluate test images, test label, or getting the test loss and test accuracy. Yeah, I'm not sure what it is it does. But basically, getting the test images. So, okay, we're gonna put the test images right now. Okay, test accuracy. Okay, to evaluate test accuracy. Oh, okay. So this is just the evaluate. Got it. Test images. Okay, 97%. Okay. So it's a bit lower than the training, right? This gap between training accuracy and direct accuracy is an example of overfitting. Okay. So if it's lower, you can kind of say it's a bit overfitting because it just means that your work really works on the training data, right? Which means it's if you're thinking about a curve, right? Because a neural network is basically a curve fitting model, right? It's just an amazing curve fitting algorithm, right? So the curve will go on every points that you can think of, like really, really like squiggly, right? So remember, you have like this scatter plot, right? And you have a bunch of data, right? Like X and O, right? X and O on the scatter plot, and then you're trying and the X and O is just scatter everywhere, right? It's not just you can just draw a line, right? And then you're trying to classify basically, right, based on those scatter plot, right? How do you classify basically within 0 and 1, for example, a number 0 and 1, not 0 to 9, right? So there's just two data, X and O, which is 0 and 1, but it's all scattered around the place, right? So when you draw it, you have to like the curve has to like go like dancing up and down, probably like sideways, And if the curve overfit means it goes to every training data that it can find, right? But actually, when you deploy this curve, because the curve is already like in a specific curve, right? Think about, you can draw it in a specific curve, like like go up and down, go sideways, go to the left, go 45 degrees here and there, right? And then when you deploy this curve, and there's a model just outside that curve, which the curve didn't even touch. So this it means it's overfitting, and you want this curve to be more, this model of this curve to be more like generalized. So it's not just like going through every data points that you can find on the training set, right? Because the training set is not the whole world. There's other part of the world that this model hasn't like see, right? Which is the tests, right? And those tests, there's some tests, the test data, there are some data that are just outside. If you make the curve is so fit to just the training data, then it's called overfitting, right? I mean, it's just good on the training set, which means has a very high accuracy, but when you deploy it on the real world, put on the real testing set, on the real data, it kind of breaks down, right? So that's the idea of overfitting. And okay, so and that's a big deal in deep learning, right? You want it, and then there's the technical regularization. I think we're gonna touch on that, Robbie, in our future next episode. So here we go. So this is it says conclude our first very example. You saw how we could build and train neural network to classify handwritten digits in less than 20 lines of Python code, right? We'll go into data every moment to clarify what is really going on behind the scenes. You will learn about tensors, the data storing object going into the network, about tensor operation with layer are made of, about gradient descent, which allows our network to learn from its training example. Okay, so hopefully this tutorial it's helpful for you. I'll see you on the next session. Keep learning.